So looking at our Canvas accounts really quickly, today we are going to talk about gas laws. I'm going to give you some mnemonics and ways to remember them and help you to get those going. And we'll practice doing some of them. We won't get to all of them, but we'll practice doing some of them. Next time, and this time we're going to do Boyle's Law. We will probably move Graham's Law to next time when we're doing the molar volume of gas, because we'll be back in lab anyway, and we didn't quite have enough time to do it fifth period. So, but I gave it to you so you can put it into your lab notebook. I forgot to give you this other one. If you would like to have it before, I will put it back there, but it was just a lot of stuff. So, and there's only 4 questions for the pre-lab, so it's pretty fast and easy for that one. Okay. So we'll do those 2 labs, Graham's Law and molar volume of gas, next time. That will be back in lab, and it will be working with heavy-duty chemicals, so make sure you dress appropriately. Make sure you bring hair ties for your hair if you've got long hair. Then we'll do phase diagrams and states of change, and then we've got exothermic and endothermic heat curves. Remember, on next Friday the 12th, your lab notebooks are going to be due. They're going to come in that day that we do this lab. It's a very short lab, but today we're going to learn how to do the Logger Pro and how to do the graphing and stuff, and this one needs graphing, so you're going to have to be able to graph it quickly and print it off and put it into your lab notebook. Remember that sapling up through 6.4 and quizzes up to 6.4 are due January 12th. Okay? So make sure they're done because they're going on this term. All right, any questions with what's going on? Please make sure that you keep these dates open, 18th through the 24th, for your test days. Okay, yes?
So the last sapling is going on next?
Yes.
We have to only do 4.
You have to do 4 before Friday next week. Okay? All right. So going forward, let's start with our notes. So hopefully you got your notes up and ready to go. So these are some canisters that we were talking about kinetic energy last time. And I want to review really quickly kinetic theory, toddler rules. 5. There were 5. What were they? No volume. Constant, random, straight line motion. Elastic collisions. Don't attract or repel. Kinetic energy changes with the temperature. You got all 5. Good job. Okay, now, get real. Teenagers have 3 different rules. Have my own volume. We know about collisions. They're not elastic. And we attract and repel. Good. I want these teenagers, which are get real gases, in other words, real gases, to be more ideal. What do? There's 3 things. High temperature. Low pressure. And? Non-polar molecules. I can choose who I hang with, right? Okay, so that was just a quick review of this. Now, on this, what I've done from side to side, this is the original. I've increased the temperature here and here. Since I increased the temperature from here to here, I had to add 10 more grams to keep the pressure, or keep the volume the same. When I did that, the pressure increased. Does that make sense? Yeah, I heat it up. If I'm going to keep the volume the same, the pressure, the number of times these balls hit the wall are going to increase, right? On this one right here, I let it go. I didn't change the weight. So the pressure's the same. What happened to the volume? It increased. Okay? So if I'm going to increase the temperature, something's got to give, right? Something's got to change with it. All right, so what we're going to do today is we're going to talk about different things and how they change things, and that's where we get our gas laws. So Avogadro found out if I put a mole of gas in here, it's going to have a certain amount of pressure to keep it in a certain volume. If I put twice the amount of moles in there, I'm going to have twice the volume to have the same pressure, right? If I have 3 times, I'm going to have what? 3 times the volume to keep the same pressure. Okay, so if I change the size of the container, if I go from a big one to a small one but keep the same amount of moles in there, then they're going to hit the sides of the wall more often. That's going to increase the pressure, right? So if I take this class and put it in a room half the size, we're probably going to be knocking into each other a lot more, trying to get up and get things. Okay? You hit the side of the containers more often. It causes an increase in pressure. If I decrease the volume, pressure increases. So that's how we need to think, the kinetics of it and what actually happens to what we can measure. STP, we're going to be using this a lot. STP means standard temperature and pressure. So the ones in red right here are what we're going to be using in our gas laws. We're going to be using 273.15 Kelvin instead of Celsius. So this is a big thing. In our gas laws, we have to change to Kelvin because temperature ends up on the bottom in the gas law. So it's something divided by temperature. If we use Celsius and we have 0 on the bottom, if I have something divided by 0, what does math tell me about that? It's undefined. I can't figure it out. Okay, but we've never reached 0 Kelvin. So we're going to have a number on the bottom. And it won't be a negative number. It has to be a positive number. So there's some problems with Celsius because it has negative numbers and it has a 0. And I can't have those on the bottom. Okay, because I can't really have a negative volume. That doesn't make sense. So we have to use Kelvin. We are going to be using atmospheres, so that conversion thing that we did at the very end last time, if I'm giving something else besides atmospheres, I'm going to have to convert it into atmospheres. Now this is only true for one specific equation in there where we have to use atmospheres. All the others, as long as the pressures are in the same units, I can still put them in. But temperature always has to be in Kelvin. Okay? So that's something we need to remember. So as we're looking at the temperature scale, these are two equations that will become very helpful to us to go back and forth between Fahrenheit and Celsius and Kelvin. So we probably want to write these down. As we're looking at the Fahrenheit scale, we know that at 32 degrees, water freezes. At 212, water boils. Well, Celsius, we made it easy. 0 is where it freezes, and 100 is where it boils. Kelvin, we now have taken that a little step farther, and we won't want any negatives in our scale, so we make 273 be the point at which it freezes, and 373 be the point at which it boils. You'll notice that the divisions between each of the marks on Celsius and Kelvin are exactly the same, but they're different from Fahrenheit to Celsius. You also notice that Fahrenheit and Celsius have a degree mark, where Kelvin does not. Okay, so there's a couple things we need to worry about that are different. So, always use absolute temperature when working with gases. This is probably the third time I've told you. And always use absolute temperature when working with gases. Absolute temperature is the Kelvin scale. Okay, I can't tell you that enough, because if you put Celsius in, it'll give you a wrong answer. So let's really quickly do some calculations. Let's change 78 Kelvin to degrees Celsius. What do I need to do that? What do I need to do? Right, subtract those two, and what do we get? And that would be degrees Celsius, sorry. I was going to put Kelvin. Okay, on the next one, what do we need to do to get from Celsius to Kelvin? Add 273.15. We add that together and we get 0.15. We put a capital K, no degree sign, and it would be 9. There we go. Okay, so this should be very simple. Most of the stuff we'll be using is just going from Kelvin to Celsius. Okay, most of the stuff we'll be using, but we might have some that we do from Fahrenheit to Celsius and then to Kelvin. So, whoops, I forgot I already did these. So we erase that so it's very, really nice and pretty. There we go. Okay, now, here's where I start the mnemonics. Don't make fun of my mnemonics. They help me to remember. Hopefully they'll help you to remember. There's an easy way to remember the ideal gas law, but it's a little bit weird. So I'm sorry if I offend anybody. I really don't want to offend anybody. But ideally, you're not a pervert. Okay? All right. That's sort of weird. That's sort of awkward. Ooh. But the ideal gas is pervert. PV equals nRT. Okay? So ideally, you're not a pervert. PV equals nRT. Pervert. Got it? Okay, that's how you remember it. Now, what does that mean? Let's go find out what the ideal gas means. Let's break it down. Pressure. In pressure, this one has to be in atmospheres. So if it's in anything else, you've got to use your conversion factors and put it into atmospheres. Volume has to be, for this equation, in liters. Okay, so it has to be in liters. N is the number of moles. R is a constant that you have to memorize or know. So 0.0821 atmospheres times liters divided by mole Kelvin. And temperature, of course, has to be in Kelvin. So if you can't remember that gas constant, that would be a good thing to put on your chart. Now, this is a nice law because from this law we can get a lot of other laws. But this is the only law that has to have everything in a specific unit. All the other laws just have to have temperature in Kelvin. Okay, so that's important to note. And if I know the R, if I know what the R is and the units on R, then I know what things the rest of the ideal gas law needs to be in. Pressure in atmospheres, volume in liters, moles, of course, in moles, and temperature in Kelvin. Okay, so let's take this and let's work on getting the other equations from this. So if we take this, if we take the ideal gas law and we solve for R, because R is a constant, then I can take different readings and I'll always get R, right? So if I put them together and put them together, combine them, then I get the combined gas law. And this is what the combined gas law is. Now, oftentimes, N is not given, and so we just drop it out. But I can get that combined gas law by just solving pervnert for R and putting them next to each other, equal to each other. Okay? So that's why I was trying to show you how to get this. So combined gas law, there's really not a mnemonic to remember it, but it's just solving for R in our PV equals nRT, and then putting ones on one side and twos on the other side. Okay? Now, as we look at this, and we go forward, looking at the ideal gas or the combined gas law, like I said, a lot of times that N drops out. So if you've put N in there, right here, I would just put a circle around it to remind myself it's not always going to be there. Okay, it's not always going to be there. It's oftentimes going to be dropped out. Okay? So this is what we normally use as the ideal gas law. The reason why is when we're in lab and we're doing lab stuff, it's really hard to change the number of moles in an equation in a lab part right in the middle. Okay, it makes it more difficult. To change the volume or temperature or pressure, easy. But changing the number of moles is a little bit harder. Okay, so then we get to Boyle's law. When you hear Boyle's, what does that mean to you? Boiling, like water, like temperature, has to do with boiling, right? Well, that's what it is. We hold temperature constant. So because we hold temperature constant, temperature actually drops out of the combined gas law, and we get P1V1 equals P2V2, which is Boyle's law. Now, N could be there, but most oftentimes it's dropped out. Okay, so of all these equations we're talking about. So temperature's constant. Boyle's hold temperature constant because I want to get up there. I want to hold that boiling point to put in my macaroni and cheese or whatever. Okay, next law, Charles. Okay, I gave you a hint here. What do you think out of the King? Is he king now? I think he's just still a prince. He's still a prince. Okay, so princes are under constant pressure to do what's right, right? Okay, so this helps me remember Charles, because Prince Charles is under constant pressure. That means the pressure would have dropped out. So pressure goes away from the combined gas law. So we get V1 divided by T1 equals V2 divided by T2. Again, N could still be there, but most often isn't. Okay? They will give you moles. They'll say, I started with this many moles, but I ended with this many moles. But they usually won't do that because it's so hard to test in lab. Okay? Next one, Gay-Lussac's. Actually, it's Gay-Lussac's, but I call it Gay-Lussac's. Don't make fun of their name. It's two different guys. No, they weren't. Yeah, anyway. It was a long time ago. But the way that I remember this one is I say their name, that last name wrong. You heard me say Gay-Lussac's, right? Because sucks has to do, like when you're sucking up a straw, what are you using? What are you doing? Are you doing pressure, temperature, or volume? Volume. I think volume. I'm going to suck up some volume of chocolate milk. Okay? So I think of sucking. So I know that volume is held constant in this one. So I think of the straw. And volume drops away. So I get P1 divided by T1 equals P2 divided by T2. Okay? So you can see this is all of these ones that we've talked about so far are derived from the ideal gas law, which is how we get the combined gas law, which is how we get all these others. Okay, so I just need to know what's held constant. On this next law, this law is not derived from the combined gas law. This one I like to think of, it's Graham's law, so I think grandma. And I had a grandma that wore the oily perfume. I don't know if you've smelled it, but we would know if she'd come to our house even if we came into our house like 2 hours later, because her smell would still be there. Does that make sense? It just lingered. It was there for a long time. And so grandma's law actually has to do with how fast gases move. So the heavier gases, the old perfumes, had heavier oils in them, and so they didn't move as fast. They didn't disperse as fast. The perfumes that we have now are more like what they used to call toilettes, which disperse really fast, and they're gone. So this one is a rate or velocity of A divided by the velocity of B is equal to the square root of the mass of B divided by the mass of A, or molecular mass. Okay, we're going to be doing that lab next time, where we're working with Graham's law, and we're going to see how two gases compare. So if I wanted to compare two perfumes, I could line you guys up in a row here, and at one end have one perfume, and at the other end have another perfume, and say, okay, open them. And as soon as you heard it or smelled it, raise your hand. Not heard it, but smelled it. Raise your hand. And we could see which perfume moved faster, had lower molecular weight. Okay, we're going to do it with ammonia, which is actually we're going to use NH4OH, which becomes ammonia and leaves water behind, and hydrochloric acid. We're going to use really strong ones. We're using Q-tips instead of the cotton plugs they have here. And we're going to look for this little wisp of a circle. Now, you can sort of see the circle right here, and there's a circle right here. This is actually past when we want to see it. We want to see it when it first makes that first circle, when the gases first collide. So if you wait too long, the gases will actually spread, and you'll see that spread out like a cone or like a cylinder. So we want that first one. We're going to measure from how far we put our Q-tip in, that point to that right here, and from where the point went in here to here. So we can see how fast they move relative to each other. Okay, we'll do that next time. So to do some definitions of what's going on with Graham's law, we did this last time, but I want to really push that you understand diffusion and effusion. Diffusion is through a large space. So how fast do gases move through a large space? Random motion, kinetic energy, straight line, random motion. Okay? Effusion is how well they go through one hole, one small hole. So if it's a large molecule, it will not effuse very well, but it might diffuse over time. If it's a small molecule, the chance that it will effuse through a small hole is high, and the chance that it will diffuse through a room is very high because it's a high energy small molecule. Okay? All right. So then we get to the last one. Gee, I wish I would have been alive when this guy got credit for this law. I call it Dalton's duh law. Like, I can't believe he got credit for this. Dalton's duh law basically says the pressure total is equal to all the little parts added up. So if I put nitrogen and oxygen and chlorine gas together in a container, and I know the pressure of each of them separate, then the pressure of them in one container is the pressure added up together. Okay? We use this, and we're going to be using it in the lab we do next time, like this. We use it to find the pressure of the dry gas, because in order to capture gas, we have to bubble it through water. And when we bubble it through water, some of that water turns into water vapor and becomes water gas. And so we have to subtract that gas off the top of the total pressure in the room to figure out the pressure of the dry gas in order to be able to do our equations. Okay? And you'll either be given those in your lab or you'll have to look them up in a book. But this is the one we use the most often. However, there will be some problems that just use this that you'll have to do. Yep. Okay. All right, so this is a way when you're doing problems to see, did I get the right answer? Because we're going to be using lots of numbers, and you'll get to the end and say, okay, put it in my calculator, and here's the answer. I call it calculator throw up. And there's a reason I call it calculator throw up, because if you don't know if that answer's right, it basically is just calculator throw up. So this is a way to help you to do this. It's actually got talking in the background. Sorry, ignore that. So basically what we're going to do is we're going to put our finger on pressure. If I hold pressure constant, so put your finger on pressure, and we're going to move your paper around. Okay, if I hold pressure constant, whose law? Charles. King Charles is under constant, or Prince Charles is under constant pressure. So if I move temperature up, what happens to volume? It increases because that paper's going to tilt up. Can you see that? Okay, put your finger over temperature. Whose law? Holds temperature constant. Boyle's law holds temperature constant. So this time if I put volume up, what's going to happen to pressure? It's going to go decrease, because if I push this side up, this side's going to go down, right? Okay, so I'm going to know two things on Boyle's law. I'm either going to know two pressures, or I'm going to know two volumes, and I'm going to try and find the other one, right? So if I know that volume goes from low to high, that means it's going up, then pressure is going to go down. I better get a lower pressure than what I had originally. Does that make sense? Okay, so put your finger on volume. Whose law? Gay-Lussac's. Good, or Gay-Lussac's. Okay, if pressure goes down with Gay-Lussac's, what happens to temperature? Goes down with it. Okay, so it might not be the exact amount, but it's going to be lower than the temperature I was given originally. Okay, all right, so we can just sort of look at how that moves and back and forth. Okay, so let's do some problems. Gas law problems are story problems. I will tell you and caution you right away, take it out and give it a label right away. If it's a temperature, take it out, convert it right away. Do not wait, because you'll forget, put it into the equation and get a wrong answer. Okay, so let's do it. What is that? It's a V, and it's the first V I come to, so I'm going to go V1, 200 milliliters. Sample of oxygen is collected at 26 degrees C. What is that? First temperature I came to, and I stop here before I go on because I have to convert it to Kelvin by adding 273.15, and I get 299.15 Kelvin, right? Everybody okay with that? Okay, going on to the next one. And, it told me pressure of P1 equals 690 torr. Okay, and then it says what volume, I'm looking for V2, will the gas occupy at STP? Ooh, STP, what did we learn about STP? Standard temperature, which was 273.15 Kelvin, and standard pressure, and since I'm in torr here, I probably want it in torr, so what would be the equivalent of 1 atmosphere, because I heard it? Look at your equivalence things. 760 torr. Now, I can do that because if I have two of them, they're going to cancel out, right? Okay, I've got two volumes. I got one volume. I got two temperatures. I got two pressures. What law am I going to use? Say it louder. Combine. So I'm going to go P1V1 divided by T1 equals P2V2 divided by T2. Now, yes. I don't in this because it's not just the ideal gas law. If it was the ideal gas law, yes? Okay. Okay. So this one right here, I don't have to change. This is a good question. Remember, only for when I'm using the ideal gas law by itself. do I need to change it because of that R, and that R was in specific units. But I'm not using R here, right? So I don't have to have the specific units. Good question. Temperature always has to change to Kelvin. Any gas law, temperature has to be Kelvin. Good questions. Now, there's lots of different ways you can approach this to solve for it, depending on what math brain you like. You can solve it with the equation without the numbers in it for V2. You can plug everything in and then solve for V2. You can plug everything in, solve one side, then divide through and do whatever. How would you like to do it? What would you like to do? How would you like to do it? Yes?
Can you solve for V2 without the numbers?
Yeah, I can solve for V2 without the numbers. So basically, if I solve for V2 without the numbers, I'm timesing both sides by T2, so T2 is going to go up, and P2 will go down, right, because I divide both sides. So that would be V2 equals P1 V1 T2 divided by T1 P2. If you don't want to do that, you can go ahead and just plug the numbers in where they're at and divide. Okay, so go ahead and solve for V2. I don't care which way you do it. See what you get for an answer. And let's see if we all end up with the same answer. I'm going to go ahead and put the numbers in to this since we solve for V2. And then see if we end up with the same answers. Remember, if you're doing it this way, you need to make sure the bottom is all in parentheses after you hit your divide. Okay? V1. So our temperature Kelvin would go out, our torr would go out. We would be left with V2 equaling milliliters, and we are in, let's say that this is 200 points so we can get 3 sig figs. Anybody got an answer? Feel brave to share? 166. Do you have a second on that one? A third, yes, okay. Yay! All right, so we've got an answer. That little PTV does not work with the combined gas law. It only works with Dalton or Gay-Lussac's or Boyle's, okay? All right, so let's go to another problem. Again, let's pull stuff out as we read. What volume? What am I looking for? Volume 1, question mark. Of air measured at 1.00 atmospheres. What is that? Pressure 1. Good. Would have to be put in a bicycle tire with a 1.00 volume, liter volume. So what's that? V2. If the pressure in the bike tire is to be at 65.0 psi, what's that? Okay, I see a problem. What is it? They're not in the same unit. So I got to pick a unit. Does it matter what unit I pick? No, it doesn't, because they're going to cancel out. What unit would you like to go to? PSI? Okay. Nope, ATM. I'm going to go ATM because I got enough room right here to convert this. So if I go to ATM, it's 1 ATM. What is the PSI? 14.7 psi, and then I'm canceling out my psi, and I'm going to get atmospheres. What is the atmospheres? That's right, guys. Get 65 divided by 14. 4.42 atmospheres. Okay, so what's happening with my pressure to get to volume 1? Think of PTV. What's being held constant? Temperature's being held constant. Okay, so I'm holding my finger right here. What's happening to pressure going from P2 to P1? Because I'm trying to find V1. It's increasing? Yeah, I've got everything on this side right here, so I'm going to be going, what's happening going this way? It's decreasing, so my pressure's going down. So what should happen to my volume? It should go up, right? Okay, let's do the calculations. Whose law is this, by the way? Temperature is held constant. It is Boyle's, so P1 V1 equals P2 V2. Now, again, you can choose how to solve it. You can throw the numbers in right now, or you can solve for V1 and then put the numbers in. I'm going to do that way, because that's the way I learned how to do it. But if you want to put the numbers in first, that's okay. All right, putting numbers in. We've got P2, which is 4.42 atmospheres. We've got V1, or V2, sorry, 1.00 liters. And we've got pressure 1.00 atmospheres. By the way, doing atmospheres made it the easy way to do the math, because 1 times 4.42 is 4.42 divided by 1 is 4.42 liters. Okay, did the volume go up? Yeah. So I can check and say, yeah, it did what it was supposed to do. I got the right answer. Okay, so that PTV is a way to double check. All right, let's do another one. This time I want you to do this by yourself. See if you can pull this through. I'm going to pause the video.
Do they have that? Wait. Do they have something called coleslaw?
Go through this real quick. Let's think about that PTV again. PTV, what's being held constant this time? Temperature. So it is what? Boyle's law. So P1 V1 equals P2 V2. What's happening to the pressure? Going towards what I don't know. It's going down. That means volume again should be going up. Okay, let's double check and see what that happens. Again, I'm going to do the V2. I'm going to solve it first. That's just the way I learned how to do it. But like I said, it's not bad to just put the numbers in and solve for that way. That's okay. Yes? Yes, it does. Thank you. That should be P1. I don't know what I was doing. Thank you. All right, so we should have 3.25 atmospheres times by V1, 6.25 liters, divided by P2, 0.250 atmospheres. Atmospheres cancel. What do we get for an answer? 81.25. Okay. Liters. And that is larger than what we started with, right? So we know we did it right.
Wait a minute.
Awesome. Okay, so let's go on to another one. Okay, let's see how we do here. 3, let's have you try this one again by yourself. I think you can do this one.
All right, I got this. I will be really.
Okay, and just set it aside for a minute. We're going to do this problem. Okay, what did you figure out on this problem? What was the 3 liters? V1. Okay, what was this? Was temperature, okay? T1. Needs to be in Kelvin, so add 273.15. Okay, what is this right here? Pressure 1. And what is this? V2, good. Whoops, 50 liters. And we're trying to find pressure 2, right? So what would temperature be? It's constant, so I just go like that. I still, if it's me, I still, excuse me, I still convert it while I'm pulling stuff out of the problem, because I might come up with one at the end that says STP. So, just a sec. So what we're going to do here is we're looking again at PTV, right? Where we're holding constant temperature. What's happening as I head this way with my volume? Getting lower. So what's going to happen with pressure? It's going to go up. So P1 V1 equals P2 V2, rearranging P2 equals P1 V1 divided by V2, plugging in pressure 1.00 atmospheres times 3.00 liters divided by 0.50 liters gives us 6.0 liters. Oh, it is pressure. Thank you. Atmospheres. Liters cancel. Okay? How many got that right? Woohoo! Yeah.
Wait, I did it too.
Yes. Good. Yes.
How are we supposed to know that, like, yeah, we can guess that, like, the temperatures
It didn't change. It didn't change. They gave me this, and that didn't change. Right? They never said that I changed the temperature, so the temperature stays the same. Okay, we're going to stop notes. We're going to start there next time. So let's talk about this for a minute. Come on. Okay, so I just passed out these. I am going to pass out some other things here in just a second, but I want to show you really fast. I got to do it faster. It won't take on the recorder. So I'm going to pass out a marshmallow for each of you to have. And what I want you to do with the marshmallow is put it inside here. Then I want you to take this, and I want you to take and push it in halfway to the 30. Then I want you to put the lid on, and then I want you to play with it. Push it in, pull it out, see what happens to the marshmallow. Okay, that's it.